Hello, my name is Shruti Vinod, and this is Lab Report 2 for Physics 2212. So the purpose of this lab is to employ charge tape as a system and to compare the point charge and line charge models. So the point charge was the one from the previous lab, and the line charge is the one that we'll be doing this time. And by partitioning the tape into different segments and treating each one as a point charge, we're going to refine our estimation of the overall distribution of charge. The principles that we use are Newton's third law of reactionary forces, superposition of charges, and distributed charges. And basically, the end result or the overview of this whole thing is the charge on each tape is about 2.52 times 10 to the power -8 coulombs, and this is due to the line charge model. The main physics ideas in this lab are the Coulomb's law, which explains the relationship between two-point charges by describing electric force acting between them, and then the gravitational force on an object near Earth's surface, which is F is equal to mv, and then Newton's third law also, which states the net force acting on an object is zero, and the object will not accelerate. So the initial conditions, this is a recap. The system is the four pieces of initially uncharged clear tape, and the surroundings is a table with no external electric fields to disrupt this experiment. And here are my calculations from the previous lab. This is just to compare the point charge to the line charge model that we'll be using. Okay, so here I'll be explaining the new version of the coding. So first we start by talking about our physical constants, which is our K and our G, and we also do the mass of our tape and our estimated net charge from our previous lab. And now we start creating a new function for the electric field, and we also define how to find the electric field in this situation more descriptively. And in the we also describe how to find the gravitational force, and we talk about how to calculate the electric force on the top tape to the bottom tape and add up the forces from each piece of the bottom tape as they interact with each piece in the top tape. So we're basically cutting our top and bottom tape into infinitely small pieces like dq, and then we add them all up to find these line charges. So here, as we can see, we have the coding results, and on the right-hand side, we have our formulas derived from lecture, which is F, and then the charge. And on the left-hand side, we have the magnitude of the electric force and the magnitude of gravitational forces that are exerted by the bottom and top tape on each other. So here, we will be talking about the results and discussion. So assumptions made here were that the tape charges are the same and have equal charge, and that the total charge is the sum of the segments. And some sources of errors that could have happened is that air resistance and air current is ignored in like our coding and our calculations, and also possible electric fields induced by our hand or other things like we cannot control that. Basically, what if? What if you had modeled each of these tapes as a single point charge, like in the previous lab, and we're told to compare the estimated value of the point charge model and a line charge model? So if the tape was a point charge, we would have the same results that we acquired from the previous lab, which basically wasn't as accurate as the results of this lab. So in the point charge one, we had a result of 1.29 e to the power -8 coulombs, but with our line charge result, we had 2.52 e to the power -8 coulombs. This is more in line and less of a discrepancy. Why? Why do these estimates differ? Which value is more likely to be closer to the real value and why? So the values differ in terms of accuracy. The line charge model is basically significantly more precise because it takes smaller steps along the length of the tape rather than simplifying it as a point charge. And as I had told before, we basically cut it into infinitely small pieces and we basically sum them up through integration. And there's a lot more specifics going on here. So these aspects make this model much more closer to real life scenarios. Thank you.